So now that you've seen recursive objects, let's see how we can solve problems with recursive functions. A recursive function is a function that may call itself one or more times. And as an example, we have this recursive print function here. And if I were to call this function, it would print out down we go, then it would call itself. So we call this the recursive call. And in the first recursive call, we'd see that the same thing gets printed out again, and then a second recursive call is made. And in that second recursive call, down we go gets printed out again, and then a third recursive call is made. So you can see kind of this pattern. It's going to keep on calling itself. In fact, this function would never stop calling itself because we've never specified a condition where it should stop making a recursive call. So this would actually go on infinitely until the program were to crash. And so it would keep on printing out down we go until you get something like a seg fault here. And the reason for the program to crash here is because we've run out of space in the stack. And the particular issue when the stack runs out of space is called stack overflow. So what we're missing in this function is called a base case. A base case is what allows us to specify a condition to tell the program when to stop recursing. Base cases are essentially what helps us prevent what we just saw right there, which is a stack overflow because of an infinite recursion. So we need to specify some kind of condition that tells the program when it should stop calling itself. So we can modify the print function here to accept an input amount, and we'll use that to tell the program how many times that we want it to print out to the console. So let's assume that this amount is a non-negative integer. So if we pass in 10, we'd want it to print out to the console 10 times. So what should our base case be? So the base case is often the simplest case. It's the case that can be completed without needing to make a recursive call. So if we want to print out some amount of times, our simplest case might be to just check if the amount is 0, because then we'd know that we don't need to print anything out and we can just return. As you work more with recursive functions, you'll notice that base cases often follow similar patterns. So for numeric inputs like this one, it's often a check for the simplest or the smallest input, which is, a lot of the times it's going to be 0. For recursive structures, as we'll see in a bit, the base case often involves a null pointer check. So now we specified a base case to avoid our program from crashing by infinitely recursing. And in theory, this base case should guarantee that at some point we're going to stop recursing. But how do we know that for sure? When we make our recursive call, we got to make sure that we're simplifying our larger problem to a smaller subproblem that takes us one step closer to the base case. So if our larger goal here is to print out 10 times, then we need to think of a recursive case that simplifies our input 10 such that we can work our way closer and closer to the base case of 0. So you can see here that we've printed out down we go once here in the body. So if our goal is to print out 10 times, what that means is that now that we've printed out once, we need to print 9 more times. So we can write a recursive call to delegate that work of having to print out 9 more times. At the start, it may feel like there's a little bit of magic involved with the recursion. It's like we're delegating the work to a recursive call, but it feels kind of weird because we don't see the work get explicitly completed within the function body like we're used to. Remember, recursion is about breaking down a larger problem into simpler subproblems, and we can solve that larger problem by solving its smaller subproblems. So though we can't see all the work be performed solely within a single function call, we can take what's called the recursive leap of faith, which is to assume that the recursive call answers your subproblem. So the question you have to ask yourself is, when you write a recursive call, if it solves a smaller problem, how can you use that to help you in your goal of solving the larger problem? So taking the recursive leap of faith just means that you assume that you have the solution to the simpler subproblem, and then we can use that to solve the larger problem at hand. So taking it back to the print function. If we pass in 10 as the amount and we print out once here, we need to print out 9 more times. And more generally, we need to print 1 less time than the given amount because we're printing out once here in the function body. So we can make a recursive call on amount minus 1. And this is where we take our recursive leap of faith. Assume that this recursive call does what we expect, which is to print the remaining amount minus 1 times. Assuming it's done that, then since we've printed out once in the function body, we've accomplished our larger goal of printing to the console based on the given amount. So this function prints exactly amount number of times. And to prove it to you, let's try and track each recursive call. So if I call print 3, then the base case is going to be checked. And 3 is not 0, the base case isn't satisfied. So we're going to print out down we go once to the console. And then we're going to make a recursive call on 1 less than 3. So we're going to recurse on print 2. And then we're going to check the base case again. 2 is still not going to satisfy the base case. So you print out a second time and then make a recursive call on 1. And the same thing happens. We'll print out a third time. Down we go. And then we're going to recursively call on 1 minus 1. So that's 0. And when we call print of 0, we're going to see that we've hit our base case. And we're just going to stop recursing at this point. So at that point, we just return, and we've printed out 3 times as we intended to in our function called print3. So now let's apply what we know about recursive functions to the recursive employee object that we saw earlier. So let's say that we want to print out all of the managers of an employee. So the first thing that you should do is think about the simplest case, the base case. So the base case is the case that can be completed without needing to make a recursive call. So if our goal is to print out all of someone's managers, then in what case could we do that without needing a recursive call? Say we want to print out worky workers managers, we would need to print out all of bossy bosses managers. And to do that, we would need to print out all of chiefy chief's managers too. But notice that chiefy chief is the CEO, so they don't have a manager. So the base case could be when an employee doesn't have a manager. And in our case, that would be the null pointer check, because chiefy doesn't point to another employee object. So looking at our employee class again, when does an employee not have a manager? That would be when the manager shared pointer doesn't point to anything. In other words, when manager is null pointer. And this is a common pattern you're going to see for base cases in all sorts of different recursive problems involving recursive structures. Oftentimes, when we are working with recursive objects, like a linked list like this, the base case involves a null pointer check. So we can write our base case now. If the manager is null pointer, what do we do? Well, if our goal is to print all of the managers and there is no manager, then that means that they're the CEO. The employee that we're looking at is the CEO because they don't have a manager, and we can just print that out. We can just say the name of this employee is the CEO. Now let's write our recursive case. So if this base case wasn't true, then we know that the employee that we're looking at has a manager, so we can print out that employee's name and their manager's name. So we'll say manager of name is manager's name. What's left is we need to make a recursive call so that we can walk our way up the management hierarchy to print all of our managers' managers until we get to the CEO. So we can make a recursive call to print managers on the manager, which should handle the rest of the managers in the management hierarchy. So this is where we need to take the recursive leap of faith, because we know that within this function body, all we've done is print out the current employee and their manager. But our larger goal is to print out all of the managers in the hierarchy, not just the current employee's manager. So by taking the recursive leap of faith, we assume that this manager.printManagers call does the job for us and prints out the rest of the managers. So we know that we've completed our overarching goal. So this function will continue to print every employee's manager until it finds an employee with no manager, the CEO, in which case the base case condition will be satisfied and the function will stop recursing. So let's see this in action. So if I invoke worker.printManagers, the function will print out the worker's manager. Then it's going to make a recursive call on bossy boss, and it's going to print out their manager, and then it's going to make a recursive call on Chiefy Chief. And Chiefy Chief has no manager. You can see it doesn't point to any other employee object. So it hits the base case and it satisfies that condition. It's a null pointer. And because Chiefy Chief has no manager, it's just going to print out that Chiefy Chief is the CEO.